Bismillahirrahmanirrahim. Welcome to the fifth lecture of this online session series. And today we are going to conduct a very important topic for our programming, for a programmer point of view. And those are memory classification and a very important register, which is instruction pointer. So let's proceed with our lecture. Before we proceed towards the main topic, I want to enlist some of the facts which we already know about memory and memory segmentation. 8086 or 8088 microprocessor has 1 megabyte of memory, and all this memory is not available at a time, which means uh, a programmer cannot access all the memory instantaneously. Rather, memory is partitioned into various segments, and those segments are available for programmer whenever programmer need them. But again, each each memory segment is of 64 kilobyte. But again, those all segments are not available. Rather, only 4 segments are available. So what are those segments? We have already learned in the previous slide, but in this slide we wanted to just enlist some of the facts which are important to recall about the coming topic. So we are going to deal in this slide the very first partition, or the very first classification of memory, which is dedicated, reserved, and general memory, which is available for the use. In this diagram, the complete memory of microprocessors 8086 or 8088 has been shown. We can see this is the minimum address, 0 hex, and so on. These basically this memory proceeding towards its final address, and that is the last address, that is FF hex, or 5 times F in hexadecimal. Well, if you see this diagram, we can observe that there are several kinds of memory. For example, this is the lowest part. It shows that it is dedicated. It's overwritten here. It is, this part is reserved. Then this part comes, which is open. What is this open means? And then this part, this is dedicated, and again that part, the last part of the memories, is again reserved. So what are those? What are their purposes? We are going to learn in this topic. So the very first part is dedicated, and it ranges from 0 hexadecimal to 13 hexadecimal, as I have written here. Dedicated part is 000 hex to 00013 hex, and a part which is just joined to this particular section, which is reserved here, and it starts from 14 hex and it goes to 7F hex. I have also written here for you. So what are these? I mean, these range. I mean, first dedicated and reserved portion. These are 128 bytes, okay, and which are used to store the pointers for interrupt service routine. So that's a very important concept in microprocessors programming point of view, and one need to know what are the interrupts. So let me highlight some of the facts which are important. These are how many bytes? 128 bytes. These are how these are used, or for what purpose they are used. They are used to store the pointers, okay. And for pointers, for what thing? Pointers for interrupt service routine. So interrupt service routine is an important concept in programming. uh, I can just summarize it for this moment, but once we are going to deal with the advanced topic in the very last portion of this course, then we will be discussing interrupt as a basic topic. So interrupt service routine refers to a small program which can be called by certain interrupt to the normal routine of microprocessor, and once that program is called, that program serves for certain purpose, and once that purpose is served, then microprocessor returns to its main routine of programming or main routine of execution of instruction. Well, at this point we do not need to know that what exactly interrupts service routines do in detail, but this point we are learning that those service routines are there, those interrupt service routines are there, and they need to be stored somewhere. So pointers means address for these interrupts. So these addresses should be stored somewhere. So this is the section, this is a section of the memory which is responsible to store the pointers for interrupt service routine. And why these are again divided into two parts: first is dedicated, the other one is reserved. So the answer to this question we are going to just answer, but before we are going to answer that question, there is one more question: how these are 128 bytes? Can you just calculate how these are 128 bytes? So if anybody can, if anybody is unable to calculate, so just for them, it's how you can do it. You have to subtract, okay, just let me, yeah, you have to subtract this maximum address, sorry, this minimum address from this maximum address. 7f hex, right, minus 00 hex and plus 1. That's the formula, or you can easily say that if you are interested in the range between the two values, this is the formula to calculate the range. So you have to subtract the minimum value from the maximum value and add 1. So it becomes 80 hex in hexadecimal, and if you are going to convert that in decimal, that becomes 128 decimal. So that's how it is basically 128 bytes of location. Okay, let's learn what is this dedicated and reserved in this memory. We know that both of these are used to store the pointers for internal for the interrupt service routines. But in this slide, we are just going to deal with dedicated part. So dedicated uh, memory is just dedicated for the pointers of internal interrupts. The key point is here internal word, right? So these are storing the pointers which are used for interrupts. But what kind of interrupts? Those are internal interrupts. There are two types of interrupts here. One is internal interrupt, another is user defined interrupt. Internal interrupt means those interrupts which are defined by the designers of microprocessors, and some of the time microprocessor need some services, so these interrupts call upon and microprocessor gets service, and once those are finished, microprocessor returns to the normal procedure of programming or the execution of instruction. But there must be some place where these internal interrupts are stored, and there must be some place where the location of those addresses, the addresses of those locations will be stored. So those are the pointers for internal interrupts, and these are stored in dedicated part of my memory. And this dedicated part, look, we have two different dedicated part, that one is above as well here, but now we are talking about this dedicated part. So can you calculate how many bytes can be stored here? Of course, it's very easy. You have to just subtract this minimum value from this maximum value, which is 00 hex, and it be subtracted by from 13 hex. So plus 1 according to the formula we learned in the last slide. So it becomes 14 hex, and in decimal it becomes 20 decimal. So there are 20 bytes which are just dedicated for internal interrupts pointer, right? Again, a very important question is here: can you calculate how many pointers can be stored within these 20 bytes? First of all, you need to learn how a pointer means how many bytes of information. Remember, we have discussed this in the last section, the last lecture, when we were dealing with the data formats and data types. So pointer is how many byte of information? 4 byte of information. That means in 20 bytes, how many 4 bytes will be available? Of course, it's quite easy. 20 bytes divided by 4 bytes, so equals to 5. So there are 5 pointers, right? So there are let me clean it. So there are how many pointers? 5 pointers. So 5 pointers are there for internal interrupts, right? So these are stored here in this part. So let's deal with the reserve part. In the last slide, we learned about the dedicated memory, and now we are going to deal with the reserve part of the memory, and it ranges from 14 hex to 7F hex. I hope you can see in this diagram. So for what purpose these are used, as we learned in the last slide, the dedicated memory was used to store the pointers for the internal service routine. This time these are basically used for the user defined interrupt service pointers, right? So last slide I told you about internal interrupts. In this slide we are dealing with user defined interrupts. So there are some interrupts which can be defined by the programmer or by the user, so that according to need of certain programs, microprocessors can be called upon by the user defined interrupts, and microprocessor gets service from these user defined interrupts. And once those services are finished, or when those services are over, microprocessor can come back to is the normal procedure of execution of interrupts. But since there can be user defined interrupts, so they must store somewhere, and similarly the addresses of those locations must be known by some pointers, and those pointers are stored here in this reserve portion. Again, we are going to deal with the same questions. How many bytes of information can be stored in this reserve part of memory? So we have to subtract the minimum address from the maximum address to calculate the number of bytes, and so it's quite easy. So we are subtracting 14F from 7F and adding 1 according to the formula we described earlier. So it becomes 6P in hexadecimal plus 1, 6C in hexadecimal. So if you convert them, it becomes 108 decimal number, right? So these are how many bytes? 108 bytes of memory, which are just reserved for what user defined interrupt service pointer. These are again storing the pointers, but for what for what kind of interrupts? For user defined interrupts, right? Again, a very important question that we answered in the last slide. We have to deal with them. How many pointers can be stored in these 108? And the answer is quite similar, or the way is quite similar. We have to just divide 108 bytes by 4 bytes, because uh, one pointer means how many bytes? 4 bytes. So we have to divide 10 bytes by 4 bytes, and it becomes 27 pointers. So there can be at maximum 27 pointers which can be stored in reserve part to points for user defined interrupt. This is also setting the limit for the user defined interrupts in 8086 or 8088 microprocessor, but we are going to talk about them once we are going to deal them in advanced topic. Okay, in this slide we are going to summarize the stuff so far we have learned about reserved and the dedicated memory. We learned that there can be 5 pointers stored for internal service routines, and similarly in the reserve part there can be 27 pointers for user defined interrupts. So we are just going to add them up here in this slide. So can you calculate the maximum number of pointers which can be stored in this portion? The maximum number of pointers, I mean in total number of pointers. Okay, pointer is what? A double word, or means the 4 byte of information, right? And the number of pointers can be easily calculated, since we know that these are 128 bytes. So if we divide them by 4 bytes, it becomes 32. So there are 32 pointers which are stored in 128 bytes of location. And what we are referring to these location, this part, right? This part of the memory from dedicated to reserved. or from 0 hex to 7 hex. So that we have deal separately in the previous slides, but right now we are just trying to summarize the whole stuff. So at maximum 128 bytes and 32 pointers, right? 32 pointers can be stored within these 128 bytes of information. So in this slide, we are going to deal with the remaining part of the memory. We have already learned about dedicated and the reserved memory, but now we are going to deal with this open space. So that open space is the actual memory which is available for data and instruction storage. That means any type of data or any operand can be used to which is supposed to store in memory will be used here in open space, or any instruction means this is the space which is basically segmented in various segments. So that's the actual space available for user access. As I told you, this space is further segmented in various segments that we have already learned in the earlier, and we are going to deal with them in the coming lectures as well. So this space is original space which is available for segments, and it ranges from 80 hex to FFEF hex. So I think there is a mistake. Yes, there is a mistake. Let me correct it. It's EF. So it ranges from 80 hex to FFEF hex, and I hope you can calculate the range by just subtracting this minimum value from this maximum value, as we have done earlier in the last slide. So let's go to the dedicated part. Why this dedicated part used? These are basically how many locations? 12 bytes. I'm not going to calculate bytes here. I hope you can calculate. So 12 bytes are using dedicated to store the pointers for hardware reset jumps, like restarting the microprocessor and so like other functions. So these are just 12 bytes of information, and you can calculate in the similar way by subtracting the minimum address from the higher address, and so on. The reserve part, the last part of the memory, is the reserve part, which is ranges from 4 times FC to 5 times F. So these are how many bytes? These are just 4 bytes, and these are used for future products and promotions. These are just you can say uh, reserved for the by the Intel Corporation itself. So in 8086 these 4 bytes were available for future products, right? So that's it from for the data for the different kinds of memory. We have learned about dedicated, reserved. Those were used for interrupt service routine. Dedicated part used for internal service routine. Reserved part used for user defined service routine. This is your data storage or segments. This is your dedicated part for the hardware reset jump, and that is your reserve part for the future products by Intel Corporation. Okay, in this slide we are going to talk about a very important topic for 8086 or 8088 microprocessors programming point of view, and that is the instruction pointer, right? Instruction pointer is what? Instruction pointer is a 16-bit register, right? This is an internal register which is present in the microprocessor, and it is a 16-bit register. And what it does, it actually points to the location where the next word of instruction is stored here, right? So what does it point? It points toward the next word of instruction, right? Word means 16 bits, right? 16 bits of instruction. And what instruction we are talking about, which is about to execute, right? So we are not talking about instruction which is already in the execution. We are rather talking about the instruction which is about to execute. That means it is the next instruction or the next part of the instruction. So that next part and how long that part is, it is equal to a word. That means a 16-bit of information, and that information is part of instruction. So the next instruction which is about to execute, the next word of that instruction is pointed by this register, right? So address of that word is stored here in 16 bits in this 16-bit register, and that is known as instruction. Since instruction is a part of programmer, so that is why it is also normally referred as a program counter in many other processors, this same register is also termed as program counter. So IP, instruction pointer, program counter, both are the name of the same register, right? Remember, if you remember, the segment based address was stored in these segment registers. These are very important registers, right? They actually hold the very first byte of the segments, right? Their addresses are stored here in CS, but IP is pointing towards the instruction. So IP is related with this register CS. CS is pointing toward the segment base of the code segment, and IP is pointing toward the next byte of the instruction, which next word of the instruction which is about to fetch. So IP and CSR both are 16-bit register, and here comes a very important topic. Normally we know that the address of a single location is 20-bit long, while we both know that IP and the CS both are 16-bit. So how these two 16 bits registers are accessing a 20-bit address? That's the mystery of 8086, and that's the beauty of 8086 or 8088 microprocessor. So we are going to learn about that thing in detail once we are going to deal with the physical memory address generation. Okay, let's enlist some of the facts which are related to the IP and the CS register. We know that the value offset in IP is combined with the current segment value of CS. What is offset? Offset means the point where actually you are in the segment, right? And CS is current segment value, which means the base address of the segment. So these two values, IP value and the CS value, IP value is the offset value and CS value is segment value or the base value, both are referring as CS colon IP. This is a very unique addressing method of 8086 and 8088. This is normally referred as a logical address, but we are going to deal with that in physical addressing generation. But now we know that this is a unique kind of address, and that is CS colon IP, and that is the address of the next instruction, right? That microprocessor is about to fetch. So microprocessor fetches instruction for C from CS. And here CS means not this register. CS means the segment, code segment. So this CS is not this CS, right? This is not this CS because this is CSR originally. If you remember, I told you this is CSR, code segment register, but we are talking about code segments, right? We are talking about code segment itself. So uh, uh, microprocessor fetches the instruction from the code segment using this address, which is CS colon IP. Store that particular instruction where in instruction queue. If you remember bus interface unit is fetching the information and storing it in instruction, and once those instructions are queued in the instruction queue, then those are executed one by one. So this is the procedure of microprocessor execution. We are going to see it in more detail. Well, every time instruction word is fetched, that means a word is fetched. Why? Because if that is quite easy to answer from at this stage, because we are talking about 16-bit register. Since it is a 16-bit 16-bit microprocessor, since it is a 16-bit microprocessor, so every time a word is fetched, right? A word is fetched. Well, every time instruction is fetched, IP is incremented by 2. For example, if its value was 0, next time value will become 2. If its value was 4, its value will become its value was 2, so it becomes 4, and so on. So every time an instruction is fetched, it increment by 2. And here comes why by 2, because we are accessing 2 bytes at a time, a word of information. So we have to point, for example, okay, yeah, these are 4 locations. This was pointed out, so this byte of information and this byte of information is already fetched. We were here at this location 0, 1 and 2. Since along with this 0 byte, 1 byte is also fetched, so we are fetching 2 bytes at a time. So this address is supposed to increment by 2. So next time these 2 bytes will be fetched, right? 2 and 3. So that is why IP is incremented by 2. Okay, in this slide we are going to see the execution of each instruction since it is being fetched using this IP. So prefetch of instruction in instruction queue up to 6 bytes in 8088, or up to 4 bytes in case of 8088, right? So 6 bytes instruction queue is present in 8086, and 8088 microprocessor 4 bytes of instruction queue. So depending upon which microprocessor we are talking about, but the function of this instruction queue remains same, right? So whenever instruction is read from the output of instruction queue, what actually happens? It is decoded. First of all, that was very first step. It has to be decoded so that microprocessor can understand what it is supposed to do. And in the next step, operands are also read from memory or internal registers if these are needed. For example, we come to know that we have to add 2 numbers, and those 2 numbers are stored in somewhere in the memory. So we may have to need we may need some memory access, or maybe those operands are stored in internal register in case of A, B, C in data register. So those values may be needed. So operations is performed as indicated by instruction. If it was written that you have to perform addition, addition is performed. If it was resulted that, if it was decoded that you have to perform the subtraction, so subtraction is performed. Thus whatever the operation which is dictated by instruction, it is performed, right? And then results are evaluated, and once results are evaluated, those results has to send somewhere, right? Those results must be written somewhere in the memory or either in the register. So it depends whatever the operation says. Then processors goes for next instruction. So this whole procedure is done while one instruction is being fetched, right, and decoded, and so on, execution is going on. So whatever these information is being fetched and resulting in IP will point always towards the next byte of information which is going to fetch in the next sequence, right? Execution may result in view of okay, that's an interesting fact. It may happen that during the execution of whatever the last instruction says, uh, during the execution, remember that was the execution, so during this execution it may happen some of the internal register may change, right? And if you remember, CS is itself a new an internal register. So it may happen a new result, new value to CS. For example, its value was 0024, right? 24, right? So maybe in after the execution this value has become now 00124. So what does it mean? It means you have a new code segment. So remember, that is kind of change of code segment. So this may also be done using that instruction. So within the execution of single instruction, we may have a change of code segment. So that is some of the things which we have to deal while we are dealing with instruction pointer values and the code segment values. Okay, that's it for this lecture. I hope you have understand the concepts that we have explained during this lecture. If you have any query, note it down for the question answer session, and we will try to resolve those queries within that question answer session. Thank you so much.